Dear students, so today let us discuss about the types of lattice in 3 dimension. In the last class we have seen the possible structures which are possible in the 2 dimension. There were 4 types of crystal structures, lattices in 2 dimension. There were square, rectangular, hexagonal and oblique. But in nature, the objects are 3-dimensional objects. All the existing 3-dimensional objects can be classified into 7 types of lattices, and they are known as the Bravais lattices, on the name of the scientist who introduced the concept of this concept. So the 7 types of crystal structures are cubic. The first one is cubic. Then tetragonal shape we have orthorhombic, trigonal or rhombohedral, then hexagonal, monoclinic and triclinic. These are the major types of crystal structures found in nature, and these are the 7 crystal structures found in nature, and they are classified into 14 types of different types of lattices, and they are known as the Bravais lattice. These are the crystal structures, and this the subtypes, including the subtypes, are known as the Bravais lattices. So first of all, we can discuss about the cubic structure. In cubic structure, we can see 3 types of cubic structures are possible. First one is the simple cubic, then body-centered cubic and face-centered cubic, that you already know. In simple cubic, this is a structure. This we have atoms only at the 8 corners. Then in the base BCC, base-centered cubic, we have one more atom is at the center besides the atoms at the corners. And in the FCC, we have atoms at the corners and also at the faces, and each face is shared by 2. So from one face we have a contribution of half to the total number of atoms. Then another type is there, that is the base, which is also known as the base-centered cubic. Base-centered cubic, we have atoms at the corners, 8 corners we have, and 2 more lattice points are there at the 2 bases only. 2 bases only instead of the face-centered. Here on 6 faces we have lattice point, but here only on 2 faces, opposite faces, we have base-centered. That can be depending upon the nature. It can be on the 3 types of opposite faces are there. So depending upon they are sometimes called A, sometimes called B, and sometimes called C. So in this case, in the cubic structure, we have 3 types only, that is simple, base-centered cubic and face-centered cubic, and the conditions are the crystal lattice translation vectors, that is A is equal to B is equal to C. These are the 3 translation vectors. You can see here these are mutually perpendicular. Then here we have the translation angle. These crystal angles we have, they are characterized by alpha, beta and gamma. All these are equal to 90 degree, and the angle between A and B, or alpha is the angle between opposite to A or between B and C. Beta is the angle opposite to B or between A and C, and gamma is the angle between which one, A and B, or opposite to the side C. So depending upon that, these are the lattice parameters. So depending upon that, first type of crystal structure is the cubic structure. Out of this we have simple cubic, body-centered cubic and face-centered cubic. In this case, the total volume, all the sides are equal, so the total volume is equal to a cube. Now the second type is tetragonal shape. In the tetragonal shape crystal structure, we have 2 types, simple and body-centered, in which A is equal to B, not equal to C, alpha is equal to beta is equal to gamma equal to 90 degree, and the volume is A square C. And the third type is orthorhombic, in which 4 possibilities are there. Simple orthorhombic, body-centered, face-centered and base-centered is there, in which A not equal to B not equal to C, alpha equal to beta equal to gamma equal to 90 degree, and the volume is of this unit cell is equal to ABC. Then in the fourth type we have trigonal, in which only one possibility is there, that is the simple trigonal, which is A is equal to B is equal to C, and alpha is equal to beta is equal to gamma, which is not equal to 90 degree. The volume is a complex one, that is A cube into root of 1 minus 3 cos square alpha plus 2 cos cube alpha. Then the fifth type is hexagonal type. So it consists of only one type of hexagonal structure, that is symbol, in which A is equal to B, not equal to C, alpha equal to beta equal to 90 degree, and gamma is equal to 120 degree. This is hexagonal structure in which the volume is equal to 3 root 3 A square C divided by 2. Then the sixth type is monoclinic, in which two possibilities are there. First one symbol cubic and the second one base centered, in which A not equal to B not equal to C, alpha is equal to gamma is equal to 90 degree, which is not equal to beta, and the volume of the crystal lattice or the unit cell is equal to ABC sin beta. Then the seventh type of crystal lattice is a triclinic, in which only one possibility is there, that is A not equal to B not equal to C, and alpha not equal to beta not equal to gamma, and the volume is ABC into root of 1 minus cos square alpha minus cos square beta minus cos square gamma plus 2 cos alpha cos beta cos gamma. So you can see here 3 plus 2 plus 4 plus 1 plus 1 plus 1 2 plus 1. So you can add this and you will get 14 types of lattice types we are getting, and they are known as the Bravais lattices. So all the solids found in nature can be classified into these 14 types of crystal lattice type, or 14 types of Bravais lattices. Okay, so that is about the space lattices. Now we can come to the case of how can we find out the volume of the a particular unit cell if we are provided with certain quantities. So for this we have a cubic unit cell. We have a cubic unit cell of lattice constant A. We have a cubic unit cell of lattice constant A, which is given in meter. Cubic unit cell, so all the sides are equal, and N is the number of atoms per unit cell. Number of atoms per unit cell is given as N. Rho be the density of the crystal material, and M be the atomic or molecular weight of the material. These are the quantities which are given. Then 1 gram of any substance contains Avogadro number of atoms. So if it is 1 kilogram of mole of substance, substance contains how many atoms? That is 6.023 into 10 raised to 26 atoms, that we can mark it as N. So mass of N atoms per molecules, that is equal to M kilogram. Therefore mass of unit cells containing N atom is M divided by Na into Nm. So from this mass of N unit cell containing N atoms, rho suppose we have to find, which is equal to mass of the unit cell divided by volume of the unit cell. Mass of the unit cell becomes M into N. Mass of the N atoms, mass of the unit cell is this one. So divided by Mn divided by Na divided by volume of the unit cell, it is V. So rho is obtained as Mn divided by Na into Aq. This is an important equation. Using this equation you have to find out the density of certain types of crystals, or this N. What is this? N stands for, N is the number of atoms per unit cell. You can find out the number of atoms per unit cells. You will get it as rho into Na A cube divided by M. So that A cube is equal to, from A cube is the volume of the unit cell, that is equal to Mn divided by Na into rho. So based on this you can find certain problems will be asked. Okay, so first of all, rho is the density, N is the number of atoms per unit cell, and a lattice constant A is also given. So by knowing we have this Avogadro number here. Na is not the Avogadro number as itself, it is a Avogadro number changed into the kilogram value. So it is 6.023 into 10 raised to 26 atoms. So mass of N atoms, so M kilogram of substance contains N atoms. So mass of N atoms which are contained is equal to M by Na. So 1 kilogram contains Na atoms. So N atoms, the mass of N atoms will be this M kilogram is given. So mass of unit cells containing n atoms will be this quantity. So rho is equal to mass of unit cell divided by the volume of the unit cell. So this is an important equation, you have to note this. So here mass of n atom, instead of n atom you have to put here Na atom, that is mass of this number. Mass of this number of atoms will be equal to m kilograms. So mass of Na atom or molecules will be m. Here this m is the molecular mass or molecular atomic or molecular mass, depending upon whether it is an atom or molecule. So here one A is missing. Mass of Na atom per Na atom or molecule, that is equal to m kilogram. M, therefore mass of unit cell containing n atoms, so you have to divide m by Na into n. So density കാണണമെങ്കിൽ നമുക്ക് mass of unit cell by volume of the unit cell. So you have to remember this equation, rho is equal to m into n divided by Na into a cube, where m is the molecular mass or atomic mass, then n is the number of atoms per unit cell, Na is the Avogadro number, that is number of atoms present in 1 kilogram mole of substance, not in 1 gram mole, and A is the lattice parameter or lattice constant A. Okay, then next we can discuss about the some of the simple lattices. A lattice is said to be primitive, you know, if it contains one lattice point. Example for a primitive lattice is a simple cubic. In simple cubic, all the atoms are of the same type. These all same type of atoms are arranged at the four corners. So radius will be the same. Now coordination number, it is the number of nearest neighbors that you have studied in degree classes. So each atom, the number of nearest neighbors will be this distance and this distance will be the same, but this distance will be somewhat greater. So nearest neighbor distance will be 6. That is the coordination number in this case is 6, and that is the coordination number. You have to note that term, coordination number n, that is equal to 6 here. Then nearest neighbor distance is what is the nearest neighbor distance? 2 atoms. രണ്ട് ആറ്റത്തിന് ഏറ്റവും മാക്സിമം എന്ത് ചെയ്യാൻ പറ്റും? ജസ്റ്റ് ടച്ച് ചെയ്ത് നിൽക്കുമ്പോൾ the center between one center and the other center, the distance between center of one atom to the center of the other atom will be r plus r. It will be 2 times r, and that will be equal to the lattice parameter in this case. 2r is equal to a. That is important in the case of simple cubic crystal. Next, the number of second nearest neighbor will be 12. Then volume, it is a cubic structure. The volume is a cube. Number of primitive unit cell. So volume of primitive unit cell, that is equal to a cube. Primitive unit cell ആണ്. If coordination number is less than 12, then we can say that or APF, atomic packing factor. Atomic packing factor is a measurement of how much closely packed these atoms are in the unit cell. If it is less than 74%, then it is loosely packed crystal. That is, in this case, n is equal to 6, so it is a loosely packed crystal. Then atomic packing factor, that also you have studied in your degree class. Atomic packing factor is volume of atoms in unit cell divided by volume of the unit cell, or how much part of the total unit cell is occupied by the atoms, or how much part is vacant. If the vacant space is large, then the atomic packing factor will be lesser. So most of the volume of the unit cell should be occupied by the atoms in the unit cell. So in this case, simple cubic structure, one atom, if it is of radius r, then its volume will be 4 by 3 r cube. Then unit cell volume is a cube, but the relation between a and r is 2a is equal to r cube. So is equal, 2r is equal to a. So you can substitute here 4 by 3 pi r cube divided by a equal to 2r. So 2r the whole cube. So you can substitute 2r cube get cancelled. Remaining part is pi by 6. So this is found to be 0.52 or 52%. Okay. Since the atomic packing fraction is less than 74%, here it is only 52% is the atomic packing factor here. So it is a loosely packed structure. Simple cubic is a loosely packed structure. And the example for substance having this type of structure is the polonium. Okay. The next we can continue in the next video.